Good afternoon, everyone. We're pleased today to have Katsu Ikeuchi from the University of Tokyo with us to share his recent work at Google TechTalks. Katsu is professor of the Institute of Industrial Science at University of Tokyo. He's been there since 1996. Prior to that, he was a faculty member at Carnegie Mellon and a postdoc at MIT's AI lab. Katsu is a pioneer in the field of computer vision and robotics. He currently serves as editor-in-chief of the International Journal of Computer Vision and is currently director of Microsoft's Institute of Japanese Academic Research Collaboration. Let's give a warm welcome to Katsu Ikeuchi.
Thank you very much. So today's talk is e-monument project. And what is e-monument? Basically, idea is to scan this kind of cultural heritage object and then to pass down to the next generation or areas to the remotely located areas. And why? Because monuments are priceless and irreplaceable and should pass down to the future generations and provide computer vision and computer graphics with ample frontiers. And in this particular e-monument project, there are a couple of issues. First one is how to sense such 3D data and how to make contents as well as how to communicate such huge data to remote areas and how to display. And today, I'll mainly talk about these sensing issues, and also there are two issues. One is 3D and 2D, but today, 3D sensing issues mainly. And a little bit about display too. Then what is a 3D scenario? First, from monument, 3D model is generated, and from this 3D model, image is generated. This kind of cultural heritage obtained range data from various viewing directions, 3D data processing, and generate 3D contents. And for this, we choose one of the temple called Bayon Temple in Cambodia. Let's see. There is a sound, actually.
India and the tradition of Khmer. The temple was constructed around the end of the 12th century to bring relief to the crisis in the Angkor era. It is well known for the appearance of, for example, calm smiling faces on towers and double corridors carved in beautiful, interesting relief.
Then why we are working or we choose this Bayon temple? First of all, this is 150, 150, 45, so quite big and provides a good challenge. And secondly, as video explained, beautiful and complex. And thirdly, central tower is inclining year by year, so there is a possible collapse in near future. So before collapse, it's a good idea to take 3D data. And in this 3D domain, first step is data acquisition, and since various viewing directions, we can determine relative relation merge. And of course, at each step, there is already commercially available sensors as well as softwares. Why we are working then? Well, the size of the Bayon temple provides various challenges to be solved. So let's take a look at each challenge. First of all, data acquisitions. Usually, we obtain color image and range images. And as you know, color image is we store red, green, blue image at each pixel, while range image, we store a distance from this particular pixel to physical point. And one of the and how to obtain this range image is, usually we can use laser range sensors to project laser light to the object and then measure the flight time. And from this flight time, we can determine distance. And commercially available sensors such as Mark used to work, Silex. And this kind of sensor can measure from 3 meter to up to 100 meter accuracies, 5 millimeters. And the example of the range data is this one. This is one of the range data of Nara Big Buddha. Now, of course, from Silex through Vivid, we have all range of the range sensors. Why we need to work? Well, problem is all are ground-based sensors. Basically, you bring sensor on tripod and wait a couple of minutes or a couple of seconds, then you can obtain range data. And of course, from the ground, this kind of pagoda, you can obtain all data. It is visible from ground. But due to the occlusion, some portions data is missing. And what we can do? Usually, we can build a scaffold around the object, and then we can bring such a ground-based sensor on the scaffold and digitize. But we are talking about the Bayon temple, 150 meter, 150 meter, 45 meters. Of course, you can build a scaffold, but it's not good for sightseers. So what we can do? Well, what we did was we hung laser range sensor under the balloon. Of course, by using this, we can guarantee various viewing directions. And this is a scene which we are obtaining by using balloon sensors. This is balloon. This is not important. This is important. And of course, you can guarantee various viewing directions, such as like these high positions. This is a good idea, though one problem is, of course, during the data acquisition, sensor moves. So this kind of distortion occurs. How we can solve this problem? As Mark explained, I come from Carnegie Mellon, so I have to use famous Takeo Kana's factorization method. Basically, given image sequence, by tracking each feature, theoretically, we can decompose this observation matrix into motion matrix and positional matrix. This is famous paper written by Tomashi and Kanade. But unfortunately, this method is good, though this is not so accurate as rectify laser range sensors data. What we can do? Well, for this, we think about distorted range data, image motion, and balloon motion, and we can extract 3 constraints. Later, I will explain what is 3 constraints. And by using this 3 constraints, we can set up nonlinear minimization method by using a cost function to estimate camera motions. And by using this, accurate estimation is obtained. Now, what is 3 constraints? First of all, in any case, factorization method provides you feature pointed 3D data. That may not so accurate, but in any case, that provides you 3D data. Also, factorization method provides you motion of the balloons or motion of the sensors. Also, since this TV camera on the lens sensor is synchronized to the laser signals, so we can also obtain 3D point with respect to this laser range sensors. They should be correspond. Basically, data obtained laser range sensor should correspond to the range data obtained by factorization method based on the motion parameters, if this motion parameter is correct. This is first constraint. Second constraint. Second constraint. Second constraint. This is so-called bundle adjustment. If you obtain 3D data, then by projecting back by using rotation and translation, that point should correspond observed data point. This is standard bundle adjustment. This is often used in stereo system. So bundle adjustment. Third constraint, the reason why I avoid helicopter and use balloon is balloon's motion is smooth, while helicopter has a high frequency vibrations. So we can assume sensor motion is smooth enough. So we introduce smoothness constraint. Motion of the camera is smooth. By combining these three constraints, bundle adjustment, smoothness constraint, and laser constraint, laser point should correspond to the factorization result. We can set up minimization paradigm. However, for this minimization, we need a good initial solutions, initial estimations. And original initial solution can be obtained by using factorization result that provide you motion of the sensors. So by using this initialization, we can refine motion parameter by using cost function given by these three constraints. And once we obtain precise motion parameters, by using this motion, we can recover shape. Let's take a look at the result. This is one of the range data obtained by combining image sequence obtained by TV camera mount on that particular sensor. We can rectify. It turned out this method is better when motion is severe, like this. And given this distorted range data and image sequence obtained at that time, we can rectify. Another example, this is a first one, this distorted data plus image sequence rectified. Besides this balloon sensor, we also developed a radar sensor. Combining this balloon sensor, radar sensor, and side arc, we can obtain data.
In order to scan large architectural structures, such as the Bayon temple, we have to use different types of sensors depending on the location of objects in the site. To scan the deity faces of Bayon, we used a long-range laser sensor named Cyrax. We measured each face from many positions, such as the ground, a scaffold on the roof, and a bucket lifted up by a crane. The data from different directions were integrated, and a 3D digital model of each face was built. To scan the narrow space between the terrace and the corridor, a laser sensor named Climbing Sensor, which moves vertically along a ladder, had been developed and was used. Bayon Temple is a huge architectural structure with a large number of high towers, and it is not practical to scan the upper side, especially the roofs from scaffolds. For this task, we used a balloon sensor, a laser sensor suspended under a balloon, which had been developed for this purpose. Two different types of laser sensors were alternatively equipped, depending on the distance to the target. The balloon was manually controlled by 4 ropes pulled from the ground. To minimize the effect of drift of the balloon.
So this is a story how we obtain data. Now, from various viewing directions, we obtain range data. In this case, 10,000 range images. And of course, if we are talking about 5 to 10 range images, there are commercially available alignment algorithms determine relative relations. But if we are talking about 10,000 quarter terabyte, usual software doesn't work well. So we develop various alignment algorithms based on actually Mark's thesis actually. And what is alignment? Basically, if there is two data, one data and second data make a correspondence between feature point or a data point, and then try to minimize the distance. And this is a nonlinear method. So iteratively minimize and obtain rotation and translation when two data overlap. Now, what is the issue in alignment? Well, first issue is, as I told you, huge data. Due to that, requires large amount of memory and long computational time. So we develop a two-step approach. One is quick pairwise alignment using graphics processing unit on-site for sensor planning and data checking. And it provides you initial alignment for the next step. Also, based on this initial alignment, we run parallel simultaneous alignment on PC clusters. First, why we need this quick pairwise alignment algorithms? Well, if computational time is long, student would be dead under severe sunlight, and I'll be fired from the university. And I would like to avoid such situations. So quick alignment is definitely necessary. And one of the most time-consuming portion in alignment algorithm is to search corresponding point. And that is usually n square operations. If number of bits is 6 power of 10, then computational become 12 power of 10. And that's long computational time. So we run quick, dirty algorithms. Basically, correspondence search by using graphics processing unit. And as I told you, if this is a little bit cheating because this is not precise alignment, but it's okay. This provides you initial estimations. How can we do? Basically, assign unique index color to each mesh and project that mesh to the graphics memories, like this. So each triangular patch has own colors, and that is open to the graphics processing unit memories. Now, we assume particular viewing directions. We project second image to this graphics plane and find which point this point is landed which triangular patch by checking color of the particular triangular patch. And from this color, we can define corresponding mesh number with respect to this particular point. By doing so, operation become order of n. And actually, number of vertices is like this, and this is a computational time. Then certainly, n operation, order of n. Once we obtain this initial alignment, large data set, well, one of the issues is sequential alignment error accumulates, so we have to make a so-called global simultaneous alignment, loading all the data and determine relative relation of entire relations. But again, if we do large amount of matrix, and so we need a localization and efficient computational method. So linearization, basically cosine become 1 and sine become theta, something like this, and we linearize. And of course, this linearization only works when initial solution is correct. And that initial solution is already obtained by using previous,
What about correcting sequential solution by interpolation?
Correcting that maybe works, that maybe work. But for that you have to know which data is.
So you go all the way around and you've got this profile and this profile. You force them to match and distribute the change over the interval.
That's another way, yeah. But in our case, we did this one. And of course, this become a sparse matrix. So by using ICF with zero field in, and the computational time become drastically decreased. And third issue is memory efficiencies. And of overflow occurs. Maybe as he pointed out, if we only use a sparse number of range data, we can avoid this problem. But in our case, since we load in entire data, so if you directly load in entire data set, overflow occurs. So, however, we know from the initial alignment which data correspond to which one roughly. So we can make data-dependent groups. And each small group is assigned to each PC in the PC clusters and run in parallel manners. And the resulting corresponding result matrix is sent to the server, and the server collects all the matrix information and recalculate, and then issue another position to each client. And client again make a correspondence, like this repetitions.
A single measurement is not sufficient for modeling a huge structure like the Bayon temple. Therefore, multiple measurements from different viewpoints are required. In order to construct the entire Bayon 3D model, it is necessary to align multiple measurements. Given an initial guess of the positional relationship between two mesh models, a developing algorithm can align them as if we were putting a jigsaw puzzle together in 3D. The result is correct estimation of the positional relationship. Iteration of this alignment process constructs the 3D model. However, this alignment method aligns only two mesh models at each step. Therefore, alignment errors accumulate in one location. So we implemented a simultaneous alignment algorithm, which can align not only two, but multiple mesh models simultaneously.
And this is aligned result. It took 5 years to collect these data. However, this data is just point cloud data, and that's not mesh data yet. So for that, we need a merging algorithm. But roughly similar story, so I will skip this component. Basically, merging is to connect the two range data, and one way is to directly connect. But since this is not good, so usually what we are doing is volumetric alignment. And again, this if we directly do overflow occurs, so we run in parallel computers. And I'll skip this component. And this is a result which we obtain 150 meter, 150 meter, 45 meter Bayon temple is represented in 2 centimeter resolutions.
How strong do you think your noise is in those measurements?
Ask Mark. The noise is coming from Silax. So, but there is no noise actually. You see sometimes seems to be noise, but that's not noise. Rather, sometimes human beings. We already obtain data, including sightseer too, okay. And also trees. So not noise actually, real data. But maybe in terms of Bayon temples, Bayon models, that may be noise. But and of course, since this is 3D data. So we can enter in this 3D data. By the way, this is a 10 centimeter resolution and not 2 centimeter resolution. This is human actually. This is again human. Yeah, my student tried to remove such human data, but And this case, since our volumetric merging algorithm use 10 centimeter resolution, due to that, this kind of hole occurs. This is again humans. Yeah, because we cannot avoid, a sightseers. They pay lots of money and visit Cambodia, so. And actually, the main reason why I went, this Bayon temple was, I originally scanned Big Buddha in actually more history. When I was at CMU with Mark and Yoichi, we tried to make a model of relatively small inside object. And when I returned to Japan, well, this modeling business is interesting. So why don't you make an independent project? But object itself is worthwhile to scan. Secondly, since I know small inside object, so how about outside large object, and it's worthwhile. And there is one ideal target in Japan called Kamakura Big Buddha, roughly 5-meter big bronze Buddha sitting outside under the sunlight. So first we scan Kamakura Big Buddha. And in Japan, there is another big Buddha called Nara Big Buddha. So I also scanned Nara Big Buddha. And I exhausted the historical Big Buddha in Japan. So I went to Thailand, and I scanned Thailand Big Buddha. And then people are saying, well, neighboring country, Cambodia, there is a temple called Bayon that has 173 big Buddha. So I went Cambodia and see that temple. Then it turned out, of course, it's interesting to scan face, but also interesting to digitize entire Bayon temple. So I digitized Bayon temple. But as a side business, of course, I digitized this deity faces. And this is one of the example, Tower 50. And this Bayon temple consists of 50 towers. And each tower has 4 faces like this. So it means 200 faces. But somehow is already gone. So currently 173. And I collect all faces. And especially this one, not sensor noise, rather when religion converted from Buddhism to Hinduism, some of them try to destroy these faces. Due to that, this kind of situation occurs. So this is a 173 face library of Big Buddha in Cambodia's Bayon temple. Now, people are saying we can classify these 173 faces into 3 groups. People saying, I would like to check whether it is possible or not. So I run usual face classification program by using this range data. And it turned out, yes, we can do that. One group consists of Deva, one group consists of Devata, and one group consists of Ashura. And this line divides male and female. This line divided by God and devil. So this is a female God area. This is a male God area. This is a male devil areas. I don't know whether there is a female devil or not, but maybe. I don't know. But anyway, we can classify this 173 into Deva, Devata, Ashura. And this is a Deva, one of the typical Deva phase. This is a typical Devata phase. This is a typical Ashura phase. Now, another question or another rumor says, well, when they construct the Bayon temple, there are a couple of independent worker group exist and construct these faces. And in order to examine this conjecture or rumor, what we did was to cluster based on similarity of each faces and set up this similarity group. This is one similarity group. This is another similarity group. By the way, this number corresponding tower numbers. So as you see, near, maybe this map is, so one similarity group exists here, one similarity group exists here, one similarity group exists here, here. So similarity faces exist at proximity positions, meaning probably one worker group has a responsibility of this area, one worker group has a responsibility of this area, like this proximity distributions. So we can safely say maybe few independent team of workers exist. And also why it resembles is another rumor says the master cave central face and then student cave by looking master's caving. Due to that, such similarity occurs. That's another rumor, and there is no documentation, just rumor, so we are not sure whether it's true or not. So what we should do is, in terms of beauty, if central one is more beautiful than peripheral areas, we can see. But right now, we have no evaluation function, which face is beautiful, which face is not beautiful. So we are investigating how to prove these conjectures. And third finding was, when we make this kind of floor plan, somehow this Bayon temple rotate 0.94 degree counterclockwise. And there is no rumor why such a situation occurred, but that's a fact. And maybe change Earth's position, or I don't know. In any case, there is 0.94 counterclockwise rotation of this entire Bayon. So these are the story of Bayon. And also, one more finding. There is many pediment exist. And maybe this pediment exists like this areas. Pediment is a kind of decoration of windows. And as I told you, this temple converted from Buddhism to Hinduism. At that time, most of this kind of window decoration is hidden. And currently, even though you visited Bayon temple, you cannot see this kind of pediment. So before us, there are no picture at all of this hidden pediment. And actually, I gave this talk at Berkeley last week. And then one of the Buddha department of Berkeley is quite excited about this pediment. And according to him, why interesting is, originally Buddha exists, but somehow they cave out and then try to put this Shiva. And by the way, this is not world premiere. This is 20 times old of world premiere. You know, maybe I gave this talk 20 or 30 times, but but relatively. And also, you know, even though you see this kind of figures, but before us, there are no picture at all. Some people try to take pictures, but they fail. And so, you know, in that sense, you know, I'm really proud of this. You know, we can generate this kind of pictures. And of course, what we did was we scanned this area, this area, this area, this area like this by using laser range sensors. And mirrors. Due to that, we succeed, actually. But this is not a low-tech solution, so I shouldn't explain too much. But anyway, a result is quite important. And especially, I didn't know that, you know, I originally thought that, well, this is not half, you know, junk, you know, decoration. But according to that professor, this is the most important figures. I don't know why. Yeah?
On the right-hand side, it seems like the faces have degraded a little bit. Were they more exposed to the weather? I'm talking about the bottom row.
Bottom row.
Yeah, those faces on the right seem to have lost their resolution, and the ones on the left seem to have higher resolution.
Well, resolution-wise, it roughly same, but there are two reasons. Maybe one is this is a rendering program, so due to the effect of rendering. Secondly, decay may occur. You know, actually, you know, this area there are lots of the bat, and due to the, you know, I don't know English name.
Birds.
Bat, B-A-T, B-A-T.
Bird.
Bat. And actually, there are lots of the residue of bats. So yeah, we clean up, but
Yeah, but it's very acidic.
yeah. Now, another issue is texturing, and maybe two issues. One is how to determine relative relation between color sensor and the laser range sensors. But this is well, one of the typical problems, so I will skip this one. Another issue is this illumination variations. And the Bayon temple is a large temple. So even though you start taking picture from here to here, when you come back, maybe dark. Due to that, color change occurs. Now, of course, in the graphic society, there are many ways to remove this kind of gap. But that doesn't provide you the real color of the surface. And why real color is necessary? Because we are talking about cultural heritage. And in terms of preserving cultural heritage, we should obtain real color, meaning we have to remove effect of sun. So issue is, first there is the illumination and heat surface, and surface spectrum is multiplied and you observe. I shouldn't say too much, but graphics is a kind of straight, not straightforward, but from illumination, multiply surface color, you obtain observation. Here, vision from obtained result, can we decompose surface color and illumination color? This is the issue. And in order to simplify the situation, we assume narrow band. Particular band is only sampled. So red means red surface and red illumination. And also, there is ambiguity in terms of intensity. If surface color is dark and illumination is strong, or if surface is brighter but illumination is dark, result is the same. So there is ambiguity in terms of brightness. So in order to cancel out this ambiguity, we use so-called chromaticity. Green channel is divided by blue, and red channel is divided by blue. Then we can cancel out this kind of illumination effect. And still, this chromaticity space, previous product of surface color and illumination color works. So now, at each point, we obtain illumination of red, we obtain R color and G color of that particular observation. But from that, we can only set up two equations, while we have 1, 2, 3, 4 unknowns. Even you can include this one, we cannot reduce the unknown numbers. So this is ill-posed problem. What we can do? We assume illumination is black body radiators. What is black body radiators? Originally, this kind of black body is heated up, then gradually its color changes. And that follows particular locus called Planck locus. And along this Planck locus, variety of illumination can be modeled as this Planck locus colors, such as snow, water, blue sky, large shadow, blue sky, and average daylight, noon sunlight, and early morning, and candlelight like this. Meaning, outdoor illumination can be modeled as black body radiation colors, Planck locus. And more importantly, inverse of this Planck locus existing particular straight line whose inclination and residue is known. And in order to verify this, actually this is pointed out in lesson. In order to verify this theory, we also took this kind of Tokyo data. And these are the blue data is obtained in our institute. And yes, they are existing this particular straight line. Now, by combining this Planck locus and previous equation, we can do a little bit better job. Now, this is an observation equation. So when you observe, you obtain IG and IR. And SG and SG, EG, SR, ER is unknown. This equation can be slightly modified like this in order to make inverse relations. So basically what I did was we divide this both term by IG and divide EG and IG. Then it turned this component is 1 over EG. 1 over EG over 1. Which one? 1 over EG. And SG over IG like this. So this is equation. And here, only IG and IR is known. Now, previous Planck locus formula, we can set up this equation too. 1 over EG equal M multiply 1 over ER plus C, where M and C is known. Of course, EG, ER is unknown. We plug in this one here, plug in this one here. Now we can set up this kind of equation where SG, IG, and multiply IG, then we can set up these equations. Here, this is observation component, observed green color and red color, and M is known values. IG is again observed color. SG, IR is unknown, meaning when you obtain one particular position's color, you can say original surface color is existing one particular straight line. We don't know where it is. We don't know where it is, but we can say that is existing one particular straight line whose inclination and bias is known. So if we obtain one particular surface color under one illumination condition, we can make one straight line. Exactly same position under different illumination conditions, we can obtain another straight line. And we are talking about surface color. So surface color never change if we are talking about the same pixel. So this intersection is real colors. Unfortunately, this method is relative, and this is a kind of the example. 1 p.m. image, 4 p.m. image, by checking exactly same positions colors, we can obtain real color of the object. This method is relatively unstable, so further we constrain. Solution area is visible area from 4,000 to 7,000 using this kind of constraint. We obtain better, more stable solutions. By the way, we are talking about this surface color under different illumination conditions, L1, L2, L3, L4, like this. So these are the input data of this particular patch. And with this particular constraint, we can obtain this estimated surface color. Wait a minute, why surface color? Maybe, I don't know. This is the true colors, and this is so this is a surface color. This is a surface color, and these are the should be color under these illumination conditions. And that is recovered by using our method and original method. And what we are saying is our method is more stable than original just straight line intersection method. Another surface patch like this, we obtain similar result. So we are claiming our method is more stable. And today I didn't explain, but our method need exactly same positions, different illumination condition. But actually, if we can assume boundary of shadows, and if we assume at the boundary bright side and the shadow side has same surface color, even from one particular image, we can obtain two illumination conditions, and we can estimate illumination color of that areas from shadows. Yeah.
Is specularity a problem in your work?
If specularity exists, solution method become much easier because specularity provides you illumination color. So the reason why we are working very hard is such as dichromatic model. Pretty much we solve the problem. But this kind of Lambertian color constancy is much more difficult than color constancy of dichromatic model actually.
Well, metal reflectors like copper don't give you the...
Okay, three story. One is Lambertian surface. One is dichromatic surface. One is copper surface. Metal surface. And metal surface, of course, we cannot handle this one, because in any case, metal surface metal surface itself has its own color, so we cannot use that method. Secondly, if surface is dichromatic surface, solution is by assuming specularity holds the same color of the illumination condition, illumination colors. So by dividing that illumination color, we can also recover body color too. And issue is how to obtain specularity point. And we also develop a method to remove. We also develop a method to detect such a specularity point. But today I'm talking about when surface is Lambertian, what kind of method can be possible. And this is one of the solutions. Okay, now so by using our method from this picture, we can rectify the color. But still, intensity is different. So by making histogram of two regions and adjust, and the intensity is obtained like this. And one of the Japanese printing company took our data and make this kind of walkthrough videos. And they are showing this video in Cambodia. I don't know why it is necessary. Well, let's skip. Did I show this one? Okay, maybe 5 more, maybe 10 more minutes. When you have this kind of 3D model, what we can do is by using this kind of 3D model, we can generate ancient roaster shape. This Nara Big Buddha originally built 8th century, but burned twice, and the current one is 16th century. So what we did was, by using current data and literature, we can obtain original Big Buddha.
The Nara Great Buddha in Todai's Temple is the most important and greatest Buddha in Japan. The 15-meter bronze Buddha image, surrounded by the Great Buddha Hall, was originally constructed in the 8th century. Unfortunately, however, several disasters critically damaged these architectural marvels. The currently existing Buddha and Great Hall were rebuilt during the 17th century. We have been attempting to restore this great cultural heritage object to its original state through the use of digital techniques. First, the current view was captured with three-dimensional laser scanning. Using the digital model and the literature survey enabled us to synthesize the original model. In May 2001, we spent 2 weeks for digitizing this great Buddha. In order to retain the higher viewpoints, scanning was done not only from the ground, but also from the ceiling. First, 180 range images were converted into a triangular-based mesh model. Then all partial mesh models were aligned together, avoiding error accumulation by using our simultaneous registration algorithm. After aligning all mesh models, our octree-based parallel volumetric view merging algorithm was applied to determine the consensus surface and generate a unified mesh model of the Great Buddha. This information is vital for cultural conservation and will be useful for further simulation of original state restoration. In the history of Japanese Buddhism, temple architectural styles have gradually changed. The current Buddha Hall, built in the 17th century, is distinctly different from the original style. Fortunately, about 100 years ago, architectural historians built a miniature of the original state according to the literature survey and a comparison of the architectures of the same period. We have also scanned this model using laser sensors. Due to the limit of the sensor's accuracy and measurement configuration, however, the final portions of the miniature cannot be acquired at a satisfactory level. Tosho Daiji Temple is a construction of the 8th century and retains the ancient styles of Buddhist architecture. In June 2001, we went to Tosho Daiji and took the partial 3D model. Totally, 780 range images were taken for 20 parts of the architecture. From the miniature model, the global positions and rough dimensions of the parts can be acquired. We extended our alignment algorithm to be able to determine the optimal scaling parameters. The miniature model was combined with parts models into the final one through this extended algorithm. The last step was the restoration of the Great Buddha. The literature survey enabled us to determine the dimensions of the original Great Buddha. The current model was morphed into the original model using these dimensions. Through digital composite morphing technology, using the archaeological knowledge, we can synthesize the original view of the Nara Great Buddha in its main hall.
Actually, this is not the end of my story. 5 more minutes is okay. Now, another issue is how to display this kind of 3D data. And of course, one way is to use this kind of dark room and show the videos. But in my opinion, this is not interesting. Rather, when you go to this kind of site, we can enjoy sunlight as well as cultural heritage too. And moreover, when you visit this kind of a heritage site, people don't appreciate this historic site at all. And rather, for example, kids visit here and just have a lunchbox and return. That's not good. And so what we did was we built this kind of virtual reality system, mixed reality system to show this kind of object on site. For this, we have to worry about a couple of issues. One is geometric consistency. Objects will appear exactly same positions. And for this, we use this kind of hardware solutions. This polyhemous device projects a magnetic field. And then from that, we know the direction of this goggles, and on this goggle we show this kind of virtual object. Then people appreciate what kind of object exists. This is a geometric solution. But the geometric solution is not enough. For example, these two objects appear exactly same position, but somehow this looks floating while this guy is on the table. And why? Because this guy doesn't have a shadow while this guy has shadows. So shadow information is again quite important. And of course, for that we have been working, and also other people are working, how to generate shadows. For example, if there is a virtual object, this portion is occluded, so this pixel only obtain partial energy, while if there is no virtual object, entire energy. So multiply this partial energy divided by entire energy to each pixel point, we can generate this kind of shadow information. And of course, for that, we have to measure illumination environment. And for that, we also develop use fisheye lens and measure the illumination environment. Actually, this is roughly same period as Paul Debek developed sphere illumination, but somehow our paper was rejected, Sigura, and his paper is in. Well, anyway. And we can generate this kind of movies, of course. But this is maybe 7 or 10 years ago, so it takes a week to calculate these videos. Now, in order to make this real time, good point is shadow under illumination ABC is shadow A, shadow B, shadow C linearization. So again, we prepare this kind of component images, and then by measuring illumination conditions, we can generate shadow on lines. But the problem of this method is, of course, we can do this kind of real-time shadows. But the problem of this method is, based on the image, so you cannot change viewing directions. So what we did was we set up this kind of shadow planes. And on this shadow plane, we calculate component images. And depending on illumination condition, we calculate current shadows. And of course, this shadow plane can be represented as a graphics processing unit as a graphics memory. So we can run in real time again. And also, we develop a method how to decompose complicated object into more simpler shadow plane. And this simpler shadow plane, we calculate component shadow images, and current illumination condition is multiplied and generate the shadows. Now, this is a hardware which we implemented. And another issue is, well, Bayon temple case, we can use 3D data of Bayon, but this particular case doesn't exist anymore. So unfortunately, we have to rely standard line drawing from CAD to CAD data. So fortunately, this site is heavily investigated by Japanese researchers. So we can obtain line drawings of ancient building. And we build this kind of CAD models. Textures. We visit all the temple, similar period, and took various pictures and paste that one and generate this one. Now, this is a complete model of that gone temple. The temple is gone already. And by combining this shadow information, we can generate this one. Now, we mount this CAD model to the previous mixed reality hardwares. And also, this is a fly-in of the ancient capital called Asuka village in Japan. Now, what we did was, this is equipment to measure illumination environment. And then if you stand in front of this virtual object and with shadow, which is reflecting current illumination environment. And even this kind of kids can enjoy. Through goggle, you can enjoy ancient appearance of this temple. And also, we build this kind of system on the hill. And from the hill, you can look down. Then you can see originally this kind of bat. On this current appearance, you can superimpose a virtual city. And in my opinion, we have to use this kind of hardware, so it's not good. So my proposal is, many Japanese companies turned down, but my proposal is, recently most of the Japanese phone has cameras. So download this kind of CAD model on this camera, depending on the position based on GPS information or something. And of course, we have to worry about geometric consistency a little bit. But when you see through this camera, if you can see this kind of ancient capital, as well as, since this is downloadable, so voice guidance, then, you know, every time we charge 1 cent or something, then but anyway, I think we should go like this direction. Now, also we are talking about maybe we should model a bicycle type, a car type, and we can convert this entire village into a kind of park. So this is today's topic, sensing issues, balance sensor, and huge data, parallel alignment algorithm, and the photometric consistency, illumination color estimation by using Planck and locus. And I burn roughly 10 million US dollar over this 10 years on this particular topic. And if you are interested in recently, by using that result, we edited a book, which consists of maybe 10 PhD theses along this line of research. So please buy this book. And also, if you are interested, visit this website. Thank you very much.